So here what we're going to have is a whole list of limit laws that we can use when we're evaluating limits, and then some examples to go with them so that we can see them applied. So these laws are valid if and only if every limit in the equation exists. So something we do have to keep in mind are cases where the limit does not exist. So that kind of happened when we had jumps in our graphs typically. So that mostly comes up with piecewise functions. There could also be with our functions going to infinity. If on one side of an asymptote it's going to negative infinity and the other side positive infinity, that's a case we want to be careful of. So there are scenarios we still want to be wary of where we may need to use a graph or tables to evaluate. What we're going to do is with these talk about how the limit does exist with each of these, and with that we can evaluate them. Now, something to be said is we're going to get to some examples in the next video of applying these limit laws, but I will say we don't have to think about these distinct limit laws each time. What we'll see is it kind of turns into this substitution of whatever x is approaching and plugging it in. It's just we can only do that because of these laws. So we're going to talk through these, and then we'll see how the laws are applied in a more general form in the next video. Okay, so let's get into it. Our first law is that if we have functions being added together and we're taking the limit as x approaches a, then we can evaluate the limit separately as x approaches a for f of x as the limit as x approaches a of g of x. So, for example, if we have x cubed plus x squared, what we could do is think of this as evaluating the limit as x approaches 1 of just the function x cubed plus the limit as x approaches 1 of just x squared. So x cubed looks like this, and if we're looking at 1, what I'm looking at is that coordinate 1, 1, and so if I was evaluating the limit as x approaches 1 of 1 cubed, really I'm looking at 1 cubed there. It's like what happens when I plug in 1. And then same thing for the limit as x approaches 1 with x squared. With our parabola, we don't have to worry about our limit not existing. We're just using that coordinate where we have our input of 1, and then our output would be 1 squared. So this is where we're going to start seeing we're plugging in and simplifying. So 1 cubed plus 1 squared is 2. So this limit lets us break up the addition and evaluate the functions individually. But then, kind of going over that piece, it's really coming down to plugging in 1 into our function, knowing that if individually our limit's going to exist everywhere, then it's going to exist everywhere for that addition of 2 functions. Okay, same thing is true for subtraction. So this would be the same as evaluating the limit of x cubed minus the limit as x approaches 2 of x squared. Again, this is going to come from the y coordinates on those graphs, so it's going to be a 2 cubed minus 2 squared, so 8 minus 4 for 4. Okay, if we have a constant multiple, so if there's a constant multiplying with our function of x, then what we can do is bring that constant out front and just evaluate the limit as x approaches a of our function. So for example, what we could do here is rewrite this as 5 times the limit as x approaches 3 of just x cubed. So we have this 5 multiplying out front, and then the limit is going to be that y coordinate of x cubed when x is approaching 3, which is going to come from 3 cubed. So 5 times 27, that should be 135. Multiplying 2 functions, we can separate the limits there. So with this, we could evaluate the limit as x approaches pi of sine of x separately from the limit as x approaches pi of cosine of x. Now those two functions defined everywhere, we can plug in, our limit's going to exist everywhere, so really this is taking sine of pi times cosine of pi. And what you're going to see is for trig, I still like to draw myself just a little picture. So pi is over here with my coordinate -1, 0. So I'm going to have my y coordinate of 0 times the x coordinate of -1, which is going to be equal to 0. All right, if we have a rational function, so a quotient where two functions are dividing each other, we could separate the limit into the numerator and denominator. We can only do this if that limit as x approaches a of that denominator function does not equal 0. So we'll look at cases in the next videos of if this happens, things we can do to adjust. But just be wary of, we don't want to plug in if it ends up with a 0 in the denominator. Okay, so with this one, what we're going to do is look at the limit as x approaches -1 of our numerator over the limit as x approaches -1 of our denominator. Okay, x squared plus 3, and we could apply the other laws of that this is addition of two functions, but what it's going to come down to is plugging in -1. So we'd have a -1 squared plus 3, and then down below, we're going to have sine of -1. And what I'm going to do here is go ahead and plug into the calculator because that's not a nice y coordinate on our unit circle. So let's go to our calculator. And what I'm going to do is make sure I'm in radian mode. So there's degree mode, radian mode, and we're going to make our fraction -1 squared plus 3 over sine of -1. And sorry, is showing degrees, so I want to switch it so it's showing radians, and there's our -4.75. Okay, just a few more laws here with composite functions. So we have our outer function of f and inner function of g. What we could do is evaluate the limit of the inner function and plug that in to our outer function f. And it only works when f is continuous at that value, which we'll talk more about continuity later on, but assume if I'm giving you a function like this, you can use this law. So this right here is a composite function because we have this inner function of x squared minus 5 and this outer function of e to the, and then its exponent. So what we could do is keep this as base of e raised to an exponent, but let's just take a look at what happens when we evaluate that limit as x approaches -2 of just x squared minus 5. And with that function there, what we would do with x squared minus 5 is we're plugging in -2. So we'll have e to the -2 squared minus 5, which is a -1. So that's going to be equal to 1 over e, and we could leave it just like that. Notice I'm continuing the limit notation until I plug in the value that x is approaching. That's when the limit notation disappears. When we're making that substitution with x equals -2, we're done evaluating the limit because this would then evaluate the limit with that value plugged in. Okay, if we have an exponent, you could evaluate the limit of the inside expression and take the exponent at the end. So what that would look like is taking the limit as x approaches 5 of just the x minus 7, and then after evaluating the limit, raising it to the third power. So what that'll look like is 5 minus 7, and then raising it to the third power, which will be a -2 cubed, so we'd have a -8. With radical functions, what we could do is evaluate the radical at the end, just like we did with exponents, because there's similar properties there. So one thing we need to be careful of, though, is if our radical is an even root, that our function is more than or equal to 0, because we can't take an even root of negative numbers. So that's one thing we need to be careful of. And if it happens when you plug in x that it ends up being negative, we would need to do some things to adjust that. So what we're going to do is take the radical at the end and just evaluate that limit as x approaches 2 of x squared plus 3x minus 5. And what that will look like is the square root of 2 squared plus 3 times 2 minus 5. So 4 plus 6 is 10, minus 5 is 5, so square root of 5. So if you take a look at these, what it comes down to is plugging in that value that x is approaching and simplifying to a single value at the end. And then what we'll talk about in the next videos is when we try to do that, if it doesn't quite work, different algebra rules, we can adjust our function so that we can get to these points of applying these limit laws.